And so now I'm going to kind of really start getting into kind of the derivations and more of the math in this chapter. So that last talk was more conceptual. So I'm going to start deriving a lot of relationships here, and there's a lot of equations in this section. So work hard at keeping track of these equations, okay? You might have to make flashcards, but there's going to be a lot of these simple little equations, and I do want you to know them. And mostly what I want you to know about these equations is, like, if I say expansion against constant external pressure, come up with the equation, okay? So we're going to have a lot of these scenarios, okay, that all end up with a different equation because the scenario gives us a different physical relationship. So in this first scenario, we have expansion work, and it's expanding against a constant external pressure, okay? So we have this, like, two cylinders. Let's say the initial state looks like this and the final state looks like this. So you can see in this scenario, the cylinder is expanding, and I'll say it's expanding by height dz, okay, from the initial to the final state. We'll also say the cylinder has area A, and that area is the same from initial to final state. And I'll also say that there is some constant external pressure pushing on this cylinder, okay? And so again, that external pressure is constant, okay? So what we can first say about this system is the following. We know that dW is negative force times dz, okay, great. And we can also say, so we really know that this constant external force is really, or constant external pressure is really the force due to gravity, right? Let's just suppose this is an open, the cylinder's open to the atmosphere, okay? So if we know pressure is force divided by area, then I can say that this force in question is going to be P external times the area. And again, I get that because I know by definition pressure is force divided by area. And so I can say then that the work that this cylinder is having to undergo is given by this force acting over this area with that constant external pressure. Okay. So I can think of the volume of the cylinder. So the cylinder is really undergoing volume changes, right? So I'll write those volume changes as dV. And remember, when I use these little d's, we're talking about infinitesimally small changes so that we can develop these relationships for any number of, subtle changes to this cylinder, okay? And so I know the volume that this undergoes, the change in volume, is going to be its area times dz. That's the change in volume, okay? And I also know that the force that this thing is undergoing is P external times area. So I can plug a few of those things in now. I can say dW has to equal negative PEXA, okay, that I get from the force, and then times dz, okay? And so now if I keep expanding on that, because I know that area times dz is just the change in volume, then I get dW is negative P external times dV, okay? And this gives me the general expression for expansion against constant external pressure, okay? So let's see what I have next. I think I added one more slide in case I need extra room, but I don't think that I need extra room yet, so let's keep going, okay? So this is our general expression, and on one of those learning goals, and I'll review that in a moment, it said know the equations for expansion against constant external pressure. This is the equation, right, that I want you to know. Because from here, you can expand that equation for analysis or for calculation, right? So for example, suppose I wanted to know how much work was done, okay? Well, if I want to know how much work is done, I have to integrate both sides. So if I integrate dw, I just get w. And now I have to integrate P external dv, and I'm going to integrate that from V initial to V final. Okay. Well, this is a pretty simple integral. We know P external is a constant, so it can just come out the other side. And then the integral of dv from V final to V initial is just going to be V final minus V initial. Okay. So that looks something like this. So work equals negative PEX times V final minus V initial. Okay. Or in other words, for this constant external pressure, right, this relationship just simply reduces to negative PEX times delta V. Okay, I put a little thick line there so you know that it's a delta. Okay? So either of these equations work, right? But you can see quite simply, because my pressure is constant, it doesn't influence this integral. Okay? So now why the negative sign? Well, let's think about this for a minute. So in this picture, we're undergoing expansion. Right? It's expanding against this constant external pressure. Okay? So now what happens to the volume? Okay? Well, volume initial is smaller than volume final. Or in other words, the quantity delta V is going to be positive in this picture. Okay? So a positive quantity times a negative quantity gives us a negative quantity. Okay? And thus expansion work is exothermic, because we recall when the sign is negative, right, that tells us it's exothermic. In other words, if this is the system and up here this P external is the surroundings, my system is pushing away the surroundings. My system is doing work on the surroundings. Okay? Well, what if it was compression? Let's see, do I have any room? So I'll write this over here. So what if it was being compressed? Well, if it was being compressed, you know, then it would go the other way, initial and final. Okay, that way. Oops, let me erase that because that's going to be confusing when you go to look at this later on. Okay, so I know what I'm going to do. Let's go to the next slide. Yes, I left myself more room. So now let's suppose, okay, let's get rid of that. Let's call this the initial and this the final. So we still, you know, have the same thing going on. This is dz, this is a, this is a. There's some constant external pressure that's the same from initial to final, right? Because it's really due to the pressure of the surroundings. And that equation said negative P external times delta V, which we know is negative P external times V final minus V initial. So in the case of compression, okay, the volume final will be smaller than the volume initial, so I get a negative term. Negative negative gives me a positive, and that is endothermic. Okay, so that means, in other words, now when the system has to undergo compression, the surroundings are pushing on the system. All right? And if we think about the work done in this scenario, I'm going to draw kind of a rather crude coordinate system, a crude graph that we'll come back to in a bit. So if I plot this as P versus V, so here's my PEX, okay? And then perhaps this is V initial and this is V final. All right, and if you look at the product of this, it's just pressure times volume. So on the scale, when I have pressure times volume, it makes a rather simple looking graph. It's just this box, okay, and the area under this curve, this box, represents, oops, let me draw a different color. Okay. So the area indicated by this box is the work done, right? Because it's just simply the product of pressure versus volume, okay? And we're always at this external pressure, right? So whether you move this way or whether you move this way, right? Whether it goes, the volume expands or whether it compresses, this total work done is the same, just opposite sign, depending on whether it's compression or expansion, okay? So now what about free expansion? I left myself a whole lot of room just to simply write work is 0 in free expansion, right? Because there's no opposing external force. So no opposing external force. So anytime a gas expands into vacuum, it doesn't do any work, okay? So that's simple enough, all right? Okay, moving on.